Alright, hello. Last class we talked about extrema and finding critical points when f prime is 0 or f prime is undefined. And then we also evaluated the left and right side of our critical points and discussed whether it was a local minimum or a local maximum. So we're going to continue discussion of 3.3 with absolute extrema. So the definition of absolute extrema, we have that let f be defined on an interval I containing c. F of c is an absolute minimum of f on your interval I if f of c is less than or equal to f of x for all x and I. And then f of c is an absolute maximum of f if f of c is greater than or equal to f of x for all x and I. So the absolute minimum, absolute maximum values of a function on the interval are sometimes just called your minimum and maximum of f on I. Our extreme value theorem, if f is continuous on the closed interval AB, then f has both a maximum value and a minimum value on AB. So before we only talked about a local max or a local min, and this was on an open interval. This with a closed interval, now we can talk about a maximum or a minimum value. So say we wanted to find the extrema on a closed interval. So to find the extremum of a continuous function on a closed interval AB, we're going to use the steps below. We're going to evaluate f at each of its critical numbers in our open interval AB. Then we're going to evaluate f at each of the endpoints. And then the least of these values is going to be your minimum, and the greatest is going to be your maximum. Okay. So let's take a look at an example. So with example 4, we want to find the minimum and maximum values of this function. Okay. So our guidelines say evaluate f of each of the critical numbers in A, in the interval. So again, this is example 4. And we're evaluating f of x equal to x squared minus 6x plus 2 on the intervals, the closed interval 0, 5. Okay. So first we want to take a look at our critical values of f. So our f prime is going to be 2x minus 6. So if we set this to 0, we have 2x minus 6 equal to 0. Let's solve for x. And divide both sides by 2. We get x is equal to 3. So again, since f prime is a polynomial, it's going to be continuous over all reals. In other words, we're not going to have an x that's going to make this undefined. So our only critical value is going to be x equals 3. So if we look at our guidelines again, first it says evaluate f at our critical numbers, and then we're going to evaluate f at each endpoint. Okay, so this tells us that we're going to evaluate f at when x is 0, when x is 3, and when x is 5. Okay. So again, we're going to make a table. So this is going to be our x value, and this is going to be f of x, and this is going to be our conclusion. Okay. So when x is 0, f of 0 is going to be, this is going to be 0 squared minus 6 times 0 plus 2. And that's going to be 2. So f of 0 is going to be 2. When x is 3, our f of 3 is going to be 3 squared minus 6 times 3 plus 2, which is 9 minus 18 plus 2, which is negative 7 plus 2 is negative 7. So f of 3 is negative 7. And then when x is 5, our f of 5 is going to be so f of 5 is going to be 5 squared minus 6 times 5 plus 2, which is 25 minus 30 plus 2. It's going to be negative 3. Okay, so from our guidelines, so it says that the least of these values is going to be the minimum and the greatest is going to be your maximum. So our least value is f of 3 equals 7. So we have the minimum is negative 7. So our maximum is 2. This is neither a maximum nor a minimum. So again, it says evaluate f at each of the critical numbers. So we looked at f prime and found them. We evaluated f also at our endpoints. Again, because it's closed, so we need to test those endpoints. The least of these values was our minimum, and the greatest was our maximum. Okay. So that'll close out section 3.2. Now we're going to move into 3.3. 3.3 is on concavity and the second derivative test. So thus far we've discussed locating the intervals on which a function f is increasing or decreasing by observing f prime. Remember, if f prime was positive, it was increasing. If f prime was negative, it was decreasing. In this section, we're going to explore how locating the intervals on which f prime is increasing or decreasing will determine where the graph of f is either curving up or curving downward. Okay. So there's a slight shift there, a slight tweak, but if you kind of watch, you'll kind of catch it. So let's do a definition of concavity. So let f be a differentiable function on an interval I. Then the graph of f is going to be concave up on I if f prime is increasing on the interval. And it's going to be concave down on I if f prime is decreasing on the interval. Okay. So if you take a look at this function on the left, if you take a look at your f prime, now although f prime is negative here, but over the function your f prime is increasing, because notice here your f prime is going to be slightly negative, then here is slightly positive, and then this one is even higher and higher. So your f prime is increasing on this one, so you have that this function is concave up here. And on the right, our f prime is decreasing. First it's slightly positive, then here your f prime is slightly negative, and then it's even more negative, so your f prime is decreasing. So this tells you that this function is concave down. So it's concave down, you have a f prime is decreasing. Now as a side note, a curve that is concave up lies above its tangent. So no matter where you draw a tangent on this interval, the function is above the tangent. So that tells you that it's concave up. This function, no matter where you draw your tangent, the function is below the tangent, so it's concave down. So let's explore how to test for concavity. So a function, let f be a function whose second derivative exists on some open interval I. So if your f double prime is positive for all x on that interval, then f is concave up. And if f double prime is negative on I, then f is concave down. And now we have some guidelines for applying concavity. So first you want to locate the x values where your f double prime is 0.